Hello and welcome to this video, which is part 2 of the description of velocity time graphs. We are dealing with how do you describe velocity time graphs? How do you describe the movement of an object if you are given a velocity time graph? And we were able to use certain terms to describe how an object moves. We were able to use terms such as velocity, speed, and acceleration. We were able to use such terms. We were able to also use the gradient of the graph at a given point, or be able to describe how the gradient of that graph is changing, hence the acceleration of the object. We are able to see that object A starts from rest and moves with uniform acceleration, or it starts from rest and moves with a velocity which is increasing uniformly. In fact, we were able to see that the velocity increases by 5 meters per second every second. So this is a uniform acceleration of 5 meters per second squared. We were also able to see how object B was described, how the motion of object B was described. It also started from rest and it moved with an acceleration which is increasing, or we were able to see that the velocity is increasing at an increasing rate. So those are some of the terms that we were able to use here. Object C again started from rest and moved with an acceleration which is decreasing, or with a velocity which is increasing at a decreasing rate, until at the 6th second it maintained uniform velocity, or a situation where the acceleration was 0. So in part 2 of this series of videos, we are going to describe more complicated motions, like for instance an object D. You can see now this object does not start from the origin, so its initial velocity is not 0, so we cannot say that it starts from rest, and we are not concerned how it was moving before we started timing. All we know is that when time is 0, its velocity is 7 meters per second. So it starts with a velocity of 7 meters per second and moves off with uniform acceleration. Are we able to determine the acceleration of this object when we are given numbers? Of course, yes. We are able to see that the initial velocity is 7 meters per second, and then after 1 second, its velocity is 12 meters per second. So you can see there is an increase of 5 meters per second. And because it is a straight line, this increase is maintained. In other words, the velocity increases by 5 meters per second every second. In other words, its acceleration is 5 meters per second squared. It's very important. I'm also showing you how to determine the acceleration of an object which is moving in a straight line very easily. All you need to check, just look at an interval of 1 second anywhere along that line, and you're able to determine, since in an interval of 1 second increases from this value to this value, then that must be the acceleration of that object throughout. Okay, so we are able to see that the acceleration of this object D is the same as the acceleration of object A. As a matter of fact, you can see that the two lines are parallel to each other. Object A and object B, the two lines are parallels. And since they are parallel, the gradient of graph A is the same as the gradient of graph D. Now, what does the gradient of a velocity time graph represent? Again, we remind ourselves that the gradient of a velocity time graph represents acceleration. So the acceleration of object A is the same as the acceleration of object D. So what is a complete description of how object D is moving? You can say this. If you want to use the terms velocity, then this is what you're going to say. Can say that the object starts with an initial velocity of 7 meters per second and moves with a velocity which is increasing uniformly. Or you can say the velocity increases by 5 meters per second every second. Now let us see how you can use the term acceleration. The object starts with an initial velocity of 7 meters per second and moves off with uniform acceleration of 5 meters per second squared. Again, we are giving that exact magnitude of the acceleration because it is possible to determine that from the numbers which are given. If by any chance these numbers are not there, then it is enough to talk about uniform acceleration. How do you know that the acceleration is uniform? It's because this is a straight line, and the gradient of a straight line is uniform throughout or is constant throughout. And furthermore, the gradient represents acceleration. That's why we are confident in saying that this object moves with uniform acceleration. Okay, having said that, let's look at object E. Object E starts with an initial velocity of 30 meters per second, and after 6 seconds, it comes to rest. It comes to rest. Notice that in this video, I'm using the term the object comes to rest. For object A, B, and C, we were able to see the term the object starts from rest. When time is 0, the velocity that the object has, of course, we can say that it starts from rest. Rest is 0. The object is not moving. Okay, but here the object starts with a velocity of 7 meters per second. Here it starts with a velocity which is 0. To describe that, we say it starts from rest. Now, object E eventually has a velocity of 0 meters per second at the 6th second. We are not concerned with how the motion is after that. All we know is that it started with a velocity of 30 meters per second and then slowed down all the way to rest after 6 seconds. Now, how does this slowing down happen? First of all, how do we know that it is slowing down? Let's check. When time is 0, its velocity is 30 meters per second. Okay? And then after 1 second, its velocity is 25 meters per second. When we look at the two magnitudes, the initial velocity was 30 meters per second. The final velocity, that is after 1 second, it's 5 seconds. We can obviously see that 25 is less than 30, so it must be slowing down. Okay? So at what rate is this velocity reducing? Because slowing down is synonymous with the velocity of the object reducing. And by the way, all these objects are moving in a straight line. They are moving in a straight line. Okay? So, the velocity reduces by 5 meters per second in 1 second. Even when you check for this other 1 second interval, you'll find that it decreases from 25 to 20 meters per second. That is a decrease of 5 meters per second in 1 second. So you can see that here the acceleration is, first of all, the acceleration is negative, but it has the same magnitude as the acceleration of object A of 5 meters per second every second. Okay, so as a matter of fact, if we were to determine the gradient of the straight line E, we are able to say that, number one, it will have a negative sign. You know, in the next video, I'm going to take you through a situation where we determine the gradient of lines on Y, on the change in Y and the change in X, as you do in mathematics. It's not different from what we are doing here. It's exactly similar. But some students end up thinking that what we talk about in physics is different from what we talk about in mathematics. There is a lot of similarity between what we talk about in mathematics and what we talk about in physics. Okay, so I want to demystify that when I look at the next video, where I go through the process of determining the gradient or the slope or the steepness of a line. You will discover that some steepness can be positive, others can be negative, others can be zero, others can be constant, others can be decreasing, others can be increasing, and so forth. We want to be very sure of how to determine the gradient of a given line. So the gradient of this line, first of all, will be negative, meaning that the acceleration will be negative. The other problem is to determine the magnitude of that negative acceleration. And we can see it's very easy. It changes from 25 to 20 in 1 second. In 1 second. Changes from 25 to 20 in a period of 1 second. So that acceleration is negative 5 meters per second squared. So when we are asked to use the term velocity to describe how the object E is moving, we'll say it starts with an initial velocity of 30 meters per second, and its velocity decreases by 5 meters per second every second until after 6 seconds it comes to rest. Okay, and this decrease in velocity is uniform, so its velocity decreases uniformly to rest. Starts with a velocity of 30 meters per second, and the velocity decreases uniformly to rest. When we say that it decreases uniformly, that does not mean that the velocity is constant or is uniform. It is the decrease that is uniform. It is the decrease that is uniform. In other words, it decreases by 5, 5, 5, 5. And you can see, since we are maintaining that magnitude 5, 5, 5, then it is uniform. So the decrease in velocity is uniform. Better still, we can use the term acceleration. We can use the term acceleration, and we can say the object starts with a velocity of 30 meters per second and decelerates to rest. Decelerates to rest after 6 seconds. And the deceleration is 5 meters per second squared. Notice that when I use the term deceleration, I don't mention the negative sign. Listen to this sentence clearly. The object starts with a velocity of 30 meters per second and decelerates uniformly to rest. Its deceleration is 5 meters per second squared. You see, there is no mention of the negative sign, because when we talk about deceleration, it means negative acceleration. If I want to use the term acceleration to describe how this object is moving, then I will say the object starts with a velocity of 30 meters per second and accelerates at minus 5 meters per second squared. And it eventually comes to rest after 6 seconds. So before we go to other complicated graphs or combination of this graph and this graph or another graph, let's first of all look at the description or how we can determine the gradient of a line on a graph. This one is important. It will help you in physics as well as remind you of what you do in mathematics all the time. So see you in the next video where I'll be talking about graphs.